can't. But it is. It's paradoxical, and yet it works.
Hello there. A battery has an EMF of 5.30 volts, negligible internal resistance. State what is meant by an EMF of 5.3 volts for this battery. So first of all, what was EMF? EMF, which is measured in volts, it's the energy transferred from other into electrical per unit coulomb. So you need to add that per unit coulomb because of the formula. So if you remember, W equals QV, V equals W over Q. So 1 volt is equal to a joule per coulomb. Okay, so now what is the other into electrical? The other depends on what it is that's providing the energy to the electron. So EMF is always energy gain. Okay, so in this case it's a battery, so it's chemical into electrical. If it was a solar panel, it would be light into electrical, and so on. Now, what's the opposite of an EMF is a PD. Now, this is not part of the answer, but I'm just going through it for completion's sake. Okay, so what is that? That's the energy transferred from electrical into other. Okay, so it's the opposite per unit coulomb. Okay, so you've got to include that per unit coulomb. Okay, now in terms of, if you think of a light bulb, it's electrical into light. If it was a heater, electrical into thermal. If it was a, let's think another, a motor, electrical into kinetic, and so on and so on. Okay, well, this one's quite specific about EMF because it says 5.3 volts. So what is 5.3 volts? That's 5.3 joules per coulomb. So what is an EMF of 5.3 volts? It's 5.3 joules of chemical energy into, and in this case, electrical, because it's an EMF. And we're going to include per unit coulomb. Okay, so that's a complete answer there. So let's move on to the next slide, or next question, sorry. Figure 13 shows the battery connected into a circuit. Okay, so the ammeter is ideal. That means the resistance is 0, which is what we want. The voltmeter is non-ideal. So the resistance of the voltmeter is not infinite. So therefore, some of the electrons are going to pass through the voltmeter, which now means there's a resistance. Okay, so, and it has a resistance R. So essentially, you've got a resistor there. Let's call it RV. Doesn't really matter what we call it. Okay, so the reading on the voltmeter is 1.05 volts when it's connected across the 320 ohms. So this is a parallel section, and they've just told you the voltage across here is 1.05 volts. So that means the voltage across any one of those branches is the same, because what do we know in parallel? The PD, or the voltage, remains the same, the current split. So we may need to know that later. But they've also told us this is 5.30 volts from the previous question. So, and then show that the reading on the ammeter is approximately 7 milliamps. Now, what you should be able to do, you should start deciphering this. So if that's 1.05 volts, that's 5.3, that's 5.30 minus 1.05. Okay, so in this case, that will be 4.25 volts. Okay, where do we get that from? Kirchhoff's second law. Sum of the EMS equals the sum of the PDs. Or, as you remember from GCSE, in series, voltage is shared. Okay, so now show that the reading on the ammeter, so they're asking for I. Now, in order to, what's your go-to formula? V equals IR. Can I use that anywhere? Can I use it as a whole circuit? Maybe. Can I use it on any individual components? Well, in order to do that, you need to know V and R in order to work out I. Well, if you look at the 640, for the 640 ohms, what have you got? You've got I is V over R, because you've got two quantities already. So you've got the V, which is 4.25 over 640. So let me just put that into my calculator. That gives me 6.64 times 10 to the minus 3 amps, which is 6.6 milliamps, which is approximately 7 milliamps to one significant figure. So we got what we wanted. So again, always sort of annotate, highlight what you have got before you worry about what you haven't got. And any part of the circuit, V equals IR, V equals IR, V equals IR. Okay, so let's move on. Sorry. That there's 6.6 milliamps going through here. And then what happens? As it does, it goes through I1, and then let's call that I2. You could flip it the other way, I2, I1, doesn't really matter. So we know it splits. You could do one or two things here. So there's two ways of going about it. So I'll do both for you. The first one is to work out I2, because you know the voltage across here. The voltage across here was 1.05 volts, wasn't it? So you know so for the 320 ohms, you could work out I2, which is V over R, which is 1.05 over R of 320. So if you did that, you don't have to do it this way, but I'm just I'll go through both in a second. So 1.05 divided by 320, and that gives you 3.3 milliamps. Okay, now what does that mean? It means the current through the other one is the difference between that and the 6.6. So if I use the exact answers, so I1 is 6.64 milli minus 3. This is actually 3.28. So we'll use the exact answers, 3.28 milliamps. So 6.64 to the xp minus 3 minus answer. Do that again. 6.4 to the xp minus 3 minus answer. So you get I1 is 3.36 milliamps exactly. Now that you know I1 and you know the voltage across it, you can work out R for the voltmeter is V over I, and it's the same voltage because they're in parallel, 1.05 over this 3.36 times 10 to the minus 3. Okay, so 1.05 divided by answer. So that gives me 312.6 ohms, or that's 313 ohms, which is roughly 300. It's debatable whether you think it's exactly that. Now, the other way you could do it is you could actually, because you've got the whole current in the circuit, you could work out for the, if I was to draw that as RV and the 320 ohm. Well, we know what you could do here, you could work out what is RT. Now, how do you work out the equivalent resistor for that? Well, you just use V over I. And you know V is 1.05, and a bit slow. And you know the current, because it's 6.64 times 10 to the minus 3. And once you've done that, once you've got RT, 1 over RT is equal to 1 over RV plus 1 over 320. So you could do it that way and work out RV that way. You'll get the same answer. So there shouldn't be any issue there. Okay. Right, so the voltmeter is now connected across the battery terminals. Calculate the power dissipated in the voltmeter. Right, so if I was to sort of draw it, what they've done, that's still 5.30 volts. And they put the voltmeter across there. Now we know the resistance of this is, we worked it out earlier to be, in fact, let me just check on the slide before. Will it let me go? No. So 300 and let me just check on my calculation. So 312.6 ohms. So, well, what's the voltage across this voltmeter now? It's now 5.3 volts, isn't it? So calculate the power. Well, you've got the V and you've got the R for it. So P equals IV, P equals V squared over R, P equals I squared R, I'll use V squared over R here. So V squared over R. And then just put the numbers in, so 5.3 volts. So the voltage has changed from 1.05 from the previous part to now 5.3 volts because it's now getting 5.3 volts because it's across the cell. So 5.30 volts squared, sorry, over 312.6 ohms. So if I put that in the calculator, I get 0.0895, and then clearly that's that was just 0.09 watts. Okay, so because the voltage across the resistor, the voltmeter resistor, has changed, then the power is going to the voltage is going to change, so the power is going to change. Right now, the reading on the voltmeter is now 2. So the reading across here now is 2.1 volts. When it was across here, it was 1.05 volts. So the question is, what's happened? Well, what they're saying is, well, why isn't 1.05 plus 2.1 equal to the EMF? And we know the EMF is 5.30 volts. Well, you have to think of it as potential dividers. So clearly, when it was here, let's just call this RT1, which is the total resistance of the parallel section, and let's call this RT2. Now, before it was, and we know this is 312.6, and that's 312.6. Well, what do we know? Well, clearly RT2 is going to be bigger than RT1, because if you did 1 over 312.6 plus 1 over the other resistor, so we know RT2 is going to be greater than RT1. Therefore, the voltage across the second one, or the new arrangement, is going to be greater than the voltage across the old arrangements. And the old arrangement was when it was 1.05 clearly. Okay, so it's that potential divider argument. So you could argue it this way, and then the other argument is, well, also the current changes because the equivalent resistances have changed. But hopefully you can see the way I've sort of numerically identified it there. Current changes because resistance in the circuit changes. So the other way to think of it is now that this one is now 2.1 volts, this isn't 1.05 anymore. This is now 5. This one is now 5.3 minus 2.1 because it's a new potential divider circuit. Okay, so that's the end of that question, I think.